Condition for perpendicular lines. Hello everyone. Welcome to today's session. We are starting a new topic titled Condition for Perpendicular Lines. Now, when we move into the realm of three-dimensional geometry, things become a bit more complex than the flat planes we are used to in 2D in this 3D space. Understanding exactly when two lines meet at a right angle or are perpendicular is absolutely essential. It is a fundamental skill you'll need when you start analyzing the spatial relationships between different objects, like edges of a cube or the intersection of planes. In this tutorial, we are going to dive into the math and specifically explain the precise mathematical condition that must be met for two lines to be considered perpendicular to each other. Let's get started. Understanding the concept. First, let's define what we mean by perpendicularity. Simply put, two lines are considered perpendicular if the angle, which we represent with the Greek letter theta, between them is exactly 90 degrees, or what we commonly call a right angle. When we move from a flat 2D plane into a three-dimensional coordinate system, this concept remains the same, but it takes on a spatial dimension. In 3D space, saying two lines are perpendicular means that the direction of one line is completely orthogonal to the direction of the other. Essentially, they are moving in directions that are perfectly square to one another. But how do we actually prove this using math rather than just looking at a diagram? To determine this mathematically, we don't look at the line's positions, but rather at their direction ratios. You can think of direction ratios as a set of specific numbers that describe the orientation or the direction of a line as it travels through space. As we will see in the next slide, these ratios are the key to deriving the formula we'll use to test for perpendicularity. Now that we've introduced our topic, let's dive into the core concept. Derivation of the condition. We'll start with the general formula used to find the angle theta between two lines. If our first line has direction ratios a sub 1, b sub 1, c sub 1, and our second line has direction ratios a sub 2, b sub 2, c sub 2, the formula for the absolute value of the cosine of theta is equal to the sum of a sub 1 times a sub 2, plus b sub 1 times b sub 2, plus c sub 1 times c sub 2, all divided by the square root of a sub 1 squared plus b sub 1 squared plus c sub 1 squared, multiplied by the square root of a sub 2 squared plus b sub 2 squared plus c sub 2 squared. To find our specific condition for perpendicular lines, we just follow a simple four-step logical process. Step 1, we set our angle theta to 90 degrees, because, as we discussed in the previous slide, that is the very definition of perpendicularity. Step 2, we evaluate the cosine of that angle. From our basic trigonometry, we know that the cosine of 90 degrees is exactly 0. Step 3, we apply this 0 back into our main formula. This gives us 0 equals the absolute value of the fraction, where the numerator is a sub 1 times a sub 2, plus b sub 1 times b sub 2, plus c sub 1 times c sub 2, over that same denominator involving the square roots we saw earlier. Step 4, now we simplify. For any fraction to equal 0, the numerator itself must be 0, as long as the denominator isn't 0. This leaves us with a very clean and powerful result. A sub 1 times a sub 2, plus b sub 1 times b sub 2, plus c sub 1 times c sub 2, equals 0. And there you have it. This is the fundamental algebraic condition we will use to test for perpendicularity in three-dimensional space. In the next slide, I'll show you a real-world way to visualize this concept. Now that we understand that perpendicularity refers to lines meeting at a right angle, let's move on to the derivation of the mathematical condition. This is where we turn that geometric concept into an algebraic rule we can actually use. Real-world analogy. Now that we have derived the mathematical formula, let's step away from the abstract algebra for a moment and look at how this concept manifests in the world around us. To visualize perpendicularity in 3 dimensions, think about the corner of a standard room. This is a perfect real-world example of 3 lines meeting at right angles. Imagine the three distinct lines formed where the walls and the floor intersect. First, there is the vertical line, which is that sharp corner edge where the two walls meet and extend up toward the ceiling. Second, consider the horizontal line where the first wall meets the floor. Finally, look at the horizontal line where the second wall meets the floor. If you observe these three edges, you will notice that each one is perpendicular to the other two. Now, connecting this back to our derivation from the previous slide. If we were to assign direction ratios to each of these three edges and apply our formula, the sum of the products of their corresponding ratios would equal 0. This confirms that the physical structure of the room perfectly obeys the mathematical condition we just learned. Worked example. Here is our problem. We need to determine whether line L1, which has direction ratios 2, -1, and 1, is perpendicular to line L2, which has direction ratios 1, 3, and 1. To solve this, we will follow a clear step-by-step process. First, let's identify our direction ratios clearly. For our first line L1, we have a 1 equals 2, B, 1 equals -1, and C1 equals 1. For our second line L2, we have a 2 equals 1, B, 2 equals 3, and C2 equals 1. Next, we move to step 2. We will substitute these specific values into the perpendicularity condition formula we derived earlier on slide 3. As a reminder, our condition is that a 1 times a 2 plus B1 times B2 plus C1 times C2 must equal 0. In step 3, we simply perform the arithmetic. Multiplying the corresponding ratios, we get 2 times 1 plus -1 times 3 plus 1 times 1. Finally, in step 4, we look at our result. When we calculate this, we get 2 minus 3 plus 1, which simplifies to 0. Because our final result is exactly 0, the condition is satisfied. Therefore, we can confidently conclude that line L1 and L2 are indeed perpendicular. Now that we have understood the theory and seen how it applies to the corner of a room, let's put this knowledge into practice with a worked example. Keep this calculation in mind, as in the next slide, we will summarize the key takeaways from this entire lesson. Key takeaways. First, it is vital to remember the fundamental definition. Two lines are considered perpendicular if, and only if, the angle between them is exactly 90 degrees. As we saw during our derivation earlier, we can translate this geometric idea into a practical algebraic rule. The mathematical condition for perpendicularity is that the sum of the products of their corresponding direction ratios must equal 0. In notation, that is, a sub 1, a sub 2, plus b sub 1, b sub 2, plus c sub 1, c sub 2 equals 0. To keep this concept clear in your mind, just remember the logic we used in our derivation. This specific condition is derived directly from the fact that the cosine of 90 degrees is equal to 0. Finally, if you are working with lines presented in vector form, using vectors b sub 1 and b sub 2, you will find that this condition is exactly the same as saying their dot product is 0. That is, b sub 1 dot b sub 2 equals 0. All right, let's wrap everything up by reviewing the key takeaways from today's lesson. Now, before we finish, I want to point out a few common pitfalls to watch out for in your upcoming practice problems. Common mistakes. First, a very common mistake is confusing points with direction ratios. When you are looking at a line, you might see coordinates for a specific point, like x, y, and z. However, to check for perpendicularity, you must use the direction ratios, which we call a b, and see it is crucial to remember that perpendicularity is all about the orientation or the direction of the lines, not where they are positioned in space. The position of the point doesn't change the angle between the lines, only the direction ratios do. Second, please be extremely careful with sign errors. As we saw in our worked example on the previous slide, you have to multiply and add several terms together, such as a sub 1 times a sub 2, plus b sub 1 times b sub 2, plus c sub 1 times c sub 2. If you accidentally miss a negative sign during this calculation, your final result won't be 0, and you'll incorrectly conclude that the lines are not perpendicular. One small slip with a minus sign can change your entire answer. Finally, don't fall into the trap of assuming that perpendicular lines must intersect. This is a unique feature of three-dimensional geometry. In 2D, perpendicular lines always meet at a right angle, but in 3D, two lines can have directions that are perfectly perpendicular even if they never actually touch. We call these skew lines. The condition we derived, where a sub 1 times a sub 2 plus b sub 1 times b sub 2 plus c sub 1 times c sub 2 equals 0, only tells us that their directions are orthogonal. It doesn't guarantee that the lines actually intersect. Now, before we wrap up today's session, I want to touch on some common pitfalls that students often encounter when working with perpendicular lines in 3D space. Being aware of these will help you avoid losing marks on exams. Keep these points in mind, and you'll be well on your way to mastering 3D geometry.